गुड मॉर्निंग, गुड इवनिंग, जिथे जो ग्रीटिंग है एक्सेप्ट करियो जिथे जो टाइम है. Good afternoon for me. Next topic is the Mandelbrot set like non-recursive mathematics? Let us now return to our earlier discussion of the Mandelbrot set. I am going to assume, for the purposes of an illustration, that the Mandelbrot set is, in some appropriate sense, non-recursive, since its complement is recursively enumerable. This would mean that the set itself would not be recursively enumerable. I think that it is likely that the form of Mandelbrot set has some lessons to teach us as to the nature of non-recursive sets and non-recursive mathematics. Let us return to figure 3.2. They are referring to some old image over there, which is 3.2, probably in chapter 3, which we encountered early in chapter 3. Notice that most of the set seems to be taken up with the large heart-shaped region, which I have labeled A in figure 4.13. The shape is referred to as cardioid, and its interior region can be defined mathematically as the set of points C of the Argand plane, which arise in the form C is equal to Z minus Z square, where Z is a complex number whose distance from the origin is less than half. This set is certainly recursively enumerable in the sense suggested earlier. An algorithm exists which, when applied to a point of the interior of the region, will ascertain that the point is indeed in that interior region. The actual algorithm is easily obtained from the above formula. Now consider the disk-like region just to the left of the main cardioid. Its interior is the set of points C is equal to Z minus 1, where Z has distance from the origin less than half, 1 by 4. This region is indeed the interior of a disk, the set of points inside an exact circle. Again, this region is recursively enumerable in the above sense. What about the other warts on the cardioid? Consider the two next largest warts. These are the roughly circular blobs which appear approximately at the top and the bottom of the cardioid, and are marked C1, C2 in image. They can be given in terms of a set CQ plus 2 square plus 1 minus 3C plus 1 minus Z square is equal to 0. That equation is equal to 0. Where now Z ranges over the region which has a distance 1/8 from the origin. In fact, this equation provides us with not merely these two blobs together, but also with the baby cardioid-like shape which appear up to the left in that image. Again, these regions constitute recursively enumerable sets by virtue of the existence of the above formula. Despite the suggestion that I have been making that the Mandelbrot set may be non-recursive, we have been able to clean out the largest areas of the set already with some perfectly well-defined and not too complicated algorithms. It seems that this process should continue. All the most evident regions in the set, and certainly the overwhelming percentage of this area, if not all of it, can be dealt with algorithmically. If, as I am supposing, the complete set is actually not recursive, then the regions that cannot be reached by our algorithms must be very delicate and hard to find. Moreover, when we have located such a region, the chances are that we can then see how to improve our algorithms so that those particular regions can also be reached. Yet, then there would be other such regions, hiding yet more deeply in the obscurities of subtlety and complication that even our improved algorithm cannot reach. Again, by prodigious efforts of insight, ingenuity, and industry, we might be able to locate such a region, but there would be yet others that would still escape, and so on. I think that this is not unlike the way that mathematics often proceeds in areas where the problems are different and presumably non-recursive. The most common problems that is one likely to come across in some specific area can be often be handled by simple algorithmic procedures which may have been known for centuries, but some will escape the net and more sophisticated procedures are needed to handle them. The ones that still escape would of course particularly intrigue the mathematicians and would goad them on to develop even more powerful methods. This would need to be based upon deeper and deeper insights into the nature of mathematics involved. Perhaps there is something of this in our understanding of the physical world. In the word problems and tiling problems considered above, one can begin to catch a glimpse of this kind of thing. Although these are not areas where the mathematical machinery has yet developed very far, we were able to use a very simple argument in one particular case to show that a certain word cannot be obtained from another by the allowed rules. It is not hard to imagine that much more sophisticated lines of reasoning can be brought into play to deal with more awkward cases. The likelihood would then be that these new lines of reasoning can be developed into an algorithmic procedure. We know that no one procedure can suffice for all the instances of the word problem, but the examples which escape would need to be very carefully and certainly constructed. Indeed, as soon as we know that how these values are constructed, as soon as we know for sure that a particular case has eluded our algorithm, then we can improve our algorithm to include that case also. Only pairs of words that are not equal can escape. So as soon as we know that they have escaped, we know that they are not equal, and that fact can be tagged into our algorithm. Our improved insight will lead to an improved algorithm. Complexity theory, that's the next topic. The arguments that I have given above is in preceding chapters concerning the nature, existence and limitations of algorithms have been very much at in principle level. I have not discussed that all the questions whether the algorithms arising are likely to be in any way practical, even for problems where it is clear that algorithms exist and how such algorithms can be constructed. It may require much ingenuity and hard work to develop such algorithms into something usable. Sometimes a little insight and ingenuity will lead to considerable reductions in the complexity of an algorithm and sometimes to absolutely enormous improvements in its speed. These questions are often very detailed and technical, and a great deal of work has been done in many different contexts in recent years in the construction, understanding, and improvement of algorithms, a rapidly expanding and developing field of endeavor. It would not be pertinent for me to attempt to enter into a detailed discussion of such questions. However, there are various things that are known or conjectured concerning certain absolute limitations on how much the speed of an algorithm can be increased. It turns out that even among mathematical problems that are algorithmic in nature, there are some classes of problem that are intrinsically vastly more difficult to solve algorithmically than others. The difficult ones can be solved only by very slow algorithms. The theory which is concerned with questions of this kind is called complexity theory. Complexity theory is concerned not so much with the difficulty of solving single problems algorithmically, but with infinite families of problems where there would be a general algorithm for finding answers to all the problems of one single family. The different problems in the family would have different sizes, where the size of a problem is measured by some natural number n. Shall have more to say in a moment about how this number n actually characterizes the size of the problem. The length of time, or more correctly, the number of elementary steps that the algorithm would need for reach a particular problem of the class would be some natural number n which depends upon smaller n. To be a little more precise, let us say that among all the problems of some particular size n, the greatest number of steps that the algorithm takes is n. Now, as n gets larger and larger, the number n is likely to get larger and larger too. In fact, n is likely to get large very much more rapidly than n. For example, n might be approximately proportional to n square or n cube, or perhaps to the 2 of n, which for large of n is very much greater than each of n cube, n square, n fourth, and n fifth. Greater indeed than n of r for every fixed number, or n might be approximately proportional to say 2 raised to power 2 of n, which is much greater still. Of course, the number of steps might depend upon type of computing machine on which the algorithm is to be run. If the computing machine is a Turing machine of the type where there is just a single tape, which is rather inefficient, then the number n might increase more rapidly than if 2 or more tapes are allowed. To avoid uncertainties of this kind, a broad categorization is made of the possible ways in which n gets large as a function of n, so that no matter what type of Turing machine is used, the measure of the rate of increase of n will always fall into same category. One such category, referred to as p, which stands for polynomial time, includes all rates which are at most fixed multiples of 1 of n, n cube, n square, n fourth, and fifth. That is to say, for any problem lying in the category P, where by a problem I really mean a family of problems with a general algorithm for solving them, we have n less than equals to k into n of r, where k and r being constants. This means that n is no larger than some multiple of n raised to some fixed power. A simple type of problem that certainly belongs to P is that the multiplying of two numbers. To explain this, I should first describe how the number n characterizes the size of a particular pair of numbers that are to be multiplied. We can imagine that each number is written in the binary notation, and n half is simply the number of binary digits of each number, giving a total of n binary digits, that is n bits in all. If one of the numbers is longer than the other, we can simply start off shorten one and with a succession of zeros to make it up to the length of the longer one. For example, if n is equal to 14, we could be considering 101010 into 00111011, and you basically multiply those in a binary system, and at some point you get a 10. The number of individual binary multiplications, n by half into n by half, is equal to n square of 4, and there can be up to n square by 4 minus n by 2 individual binary additions. This makes n square by 2 minus n by 2 individual arithmetical operations and all, and we should include a few extra for the logical steps involved in carrying. The total number of steps is essentially n is equal to n square by 2, which is certainly polynomial. For a class of problems in general, we take a mere n of the size n of the problem to be the total number of binary digits needed to specify the free data of the problem of that particular size. This means that for given n, there will be up to 2n different instances of the problem for that given size, because each digit can be one of the two possibilities, 0 or 1, and there are n digits in all, and these have to be copied with uniformly by the algorithm in a not more than n steps. There are many examples of problems which are not in P. For example, in order to perform the operations of computing 2 raised to power 2r from the natural number r, we would need about 2n steps even just to write down the answer, let alone to perform the calculation, n being the number of binary digits in the binary representation of r. The operation of computing 2 by 2r takes something like a 2 steps to write down, etc. These are much bigger than polynomials and certainly not the P note. More interesting, not in P note. More interesting are problems where the answers can be written down and even checked for correctness in polynomial time. There is an important category of algorithmically solvable classes characterized by this property. They are referred to as NP classes of problems. More precisely, if an individual problem of a class of problems in NP has a solution, then the algorithm will give that solution, and it must be possible to check in polynomial time that the proposed solution is indeed a solution. In the cases where the problem has no solution, the algorithm will say so, but one is still required to check in polynomial time or otherwise that there is indeed no solution. NP problems arise in many contexts, both within mathematics itself and in the practical world. I shall just give one simple mathematical example, the problem of finding what is called a Hamiltonian circuit in a graph. By a graph is meant a finite collection of points or vertices, a certain number of pairs of which are connected together by lines called the edges of the graph, which are not interested in geometrical or distance properties here, but only in which vertex is connected to which. Thus, it does not really matter whether the vertices are all represented on one plane, assuming that we don't mind the edge crossing over one another or in three-dimensional space. A Hamiltonian circuit is simply a closed-up route or loop consisting solely of edges of the graph and which passes exactly once through each vertex. An example of a graph with a Hamiltonian circuit drawing on it. There is a graph over there. The Hamiltonian circuit problem is to decide for any given graph whether or not a Hamiltonian circuit exists and to display one explicitly whether one does exist. There are various ways of presenting a graph in terms of binary digits. It does not matter a great deal which method is used. One procedure would be to number the vertices 1, 2, 3, 4, 5 and then to list the pairs in some appropriate fixed order, that 1, 5, 1, 2, 1, 3, 1, 4 or anything like that. Then we make an exactly matching list of zeros and ones where we put a 1 whenever the pair corresponds to an edge of a graph and 0 whenever it does not. Thus the binary sequence is 1, 0, 0, 1, 0, 1, 1, 0, 1, 1, 0. We would designate that a vertex 1 is joined to vertex 2, to vertex 4 and to vertex 5, and vertex 3 is joined to vertex 4 and to vertex 5, vertex 4 is joined to vertex 5, blah blah blah. The Hamiltonian circuit could be given, if desired, just as a sub-collection of these edges, which would be described as a binary sequence with many more zeros than before. The checking procedure is something that can be achieved much more rapidly than finding the Hamiltonian circuit in the first place. All that one needs to do is check that the proposed circuit is indeed a circuit, that its edges indeed belongs to those of the original graph, and that each vertex of the graph is used exactly twice, once at the end of each of the two edges. This checking procedure is something that can be easily achieved in polynomial time. In fact, this problem is not a NP, but it is known as NP complete. This means that any other NP problem can be converted it into a polynomial time, so that if someone were clever enough to find an algorithm which solves the Hamiltonian circuit problem in polynomial time, that is to show that the Hamiltonian circuit problem is actually in P, that it would follow all the NP problems are actually in P naught. Such a thing would have momentous implications. In a general way, problems which are in P are regarded as being tractable, that is soluble in a acceptable length of time, for reasonably large n on a fast modern computer, while problems in NP which are not in P are regarded as being intractable, that is, though soluble in principle, they are insoluble in practice, for reasonably large n, no matter what increases in operational computer speed of any foreseeable kind are envisaged. The actual time that would be taken for large n rapidly becomes longer than the age of universe for an NP problem not in P, which is not much used for the practical problem. Any clever algorithm for solving the Hamiltonian circuit problem in polynomial time could be converted into an algorithm for solving any other NP problem, whatever, in polynomial time. Another problem which is NP complete is the traveling salesman problem, which is rather like a Hamiltonian circuit problem, except that the various edges have numbers attached to them, and then one seeks that Hamiltonian circuit for which the sum of numbers, the distance traveled by salesman, is a minimum. Again, a polynomial time solution of the traveling salesman problem would lead to polynomial time solutions of all other NP problems. If such a solution were found, it would make a headline news. For in particular, there are the secret code systems that have been introduced over the past several years, which depend on a problem of factorization of large integers, this being another NP problem. If that problem could be solved in a polynomial time, then such codes could probably be cracked by the use of powerful modern computers, but if not, then those codes appear to be safe. It is commonly believed by the experts that it is actually impossible with any Turing-machine-like device to solve an NP-complete problem into a polynomial time. In fact, constitutionally, P and NP are not same. Very likely this belief is correct, but as yet no one has able to prove it. This remains the most important unsolved problem of the complexity theory. Complexity and computable in physical things. That's the next topic. Complexity theory is important for our considerations in this book because it raises another issue somewhat separate from the question of whether or not things are algorithmic, namely whether or not things are known to be algorithmic or actually algorithmic in a useful way. In the later chapters, I shall have less to say concerning matters of complexity theory than of computability, for I am inclined to think that unlike the basic questions of computability itself, the issues of complexity theory are not quite the central ones in relation to mental phenomena. Moreover, I feel that the questions of practicality of algorithms are being only barely touched by complexity theory as it stands out today. However, I could well be wrong about the role of complexity. As I shall remark later, the complexity theory for actual physical objects could perhaps be different in significant ways from that which we have just been discussing. For this possible difference to become manifest, it would be necessary to harness some of the magical properties of quantum mechanics, a mysterious yet powerfully accurate theory of the behavior of atoms and molecules, and many of other phenomena some of which are important on a much larger scale. We shall be coming into terms with this theory in chapter 6. According to the recent ideas introduced by David Deutsch, it is possible in principle to construct a quantum computer for which there are programs which are not in P yet which could be solved by that device in polynomial time. It is not all clear as of now how an actual physical device could be constructed which behaves as a quantum computer, and moreover the particular classes of problems so far considered as decidedly artificial, but the theoretical possibility that a quantum physical device may be able to improve on a Turing machine seems to be with us. Can it be a human brain, which I am talking for the discussion, to be a physical device, albeit one of the amazing subtlety and delicacy of design as well as complication is itself taking advantage of the magic of quantum theory? Do we yet understand the ways in which quantum effects might be used beneficially in the solving of problems or the forming of judgments? Is it conceivable that we might have to go even beyond present-day quantum theory to make use of such possible advantages? Is it really likely that actual physical device might be able to improve upon the complexity theory for Turing machines? And what about computability theory for actual physical devices? To address such questions, we must turn away from matters purely mathematical and ask in the coming chapters how the physical world actually behaves. So that was the chapter 4, and chapter 5 is the classical world, and we should, or I will continue from next video.